Hi, I'm Bob. Economists often try to find the causal effects of explanatory variables on the outcome variable. For example, people are very interested in the return to education. We want to know whether education has a causal effect on wages. We usually use observed data to establish a causal relationship between the hourly wage and the worker's educational attainment. The challenge of using observed data in our research is whether the estimates are unbiased or consistent estimates of the true parameter. In this OLS model, we regress wage on education, experience, race, and region variables. We have no data on the worker's ability or personality. The unobserved factors, such as the worker's ability and personality, are called omitted variables and become elements of the error term. The worker's ability and personality are likely to affect the wage they earn and also relate to the worker's educational attainment. If this is the case, the OLS estimate of the return to education will be biased. In other words, the estimate is not expected to equal the true parameter beta 1. Let me show you why omitted variables result in biased estimates mathematically. We have an OLS model relating the outcome variable y to the explanatory variable x1. Suppose the error term epsilon contains two components. One component is the omitted variable x2. In other words, the true relationship is as follows. x2 should be an explanatory variable in the model. However, it is unobserved or unmeasured, and it is omitted from the model. We write the matrix form of the OLS estimator beta 1 hat, and then replace y with the true relationship expression. Now, we have three terms. The first term is the true parameter beta 1. The second term can be written as beta 2 times the estimator from regression of x2 on x1. The third term has an expectation of 0 because the zero correlation assumption between x1 and the error term. Therefore, the expectation of the OLS estimator beta 1 hat equals the true value beta 1 plus a biased term. The term beta 2 times alpha hat is the omitted variable bias. The variable x1 is said to be an endogenous variable. We come back to our example. For a simple wage regression model, if beta 2 and alpha hat are not 0, then the OLS estimator beta 1 hat is biased. In other words, if the worker's personality influences wages and is also correlated with education, then the OLS estimate suffers from omitted variable bias. There were solutions to omitted variable bias. An unbiased causal relationship could be established in a randomized controlled experiment. In a random sample, the worker's ability and personality could be seen as randomly distributed among workers. As a result, they will not bias the estimate of the return to education. However, in economics and many other areas of social science, the randomized controlled experiments are not always feasible. We could not assign children randomly to receive different levels of education due to prohibitive costs and, most importantly, the ethical concerns. We have to figure out other approaches to alleviate the omitted variable bias problem. We have discussed the difference in differences approach in previous topics. Difference in differences is a method to tackle the omitted variable bias. In addition to difference and differences, the instrumental variables method is widely used to find unbiased and consistent estimates when omitted variable bias occurs. Using the instrumental variables method, we need to find a variable that relates to the endogenous variable, education in our example, and we use it as an instrument to find an unbiased or consistent estimate for the return to education. A valid instrumental variable must satisfy two requirements. They are the instrument relevance requirement and the instrument exogeneity requirement. The first means the instrumental variable and the endogenous variable are correlated. It can be tested in the first stage regression or the reduced form equation for the endogenous variable. The null hypothesis is that alpha equals 0. If we reject the null hypothesis, the instrument relevance requirement is satisfied. In our example, we consider using the parent's education level as an instrumental variable for the worker's education. We can regress workers' education on their parents' education and see whether they are significantly correlated. That is, whether the parent's education has a statistically significant effect on the worker's education attainment in the first stage regression. The second requirement is that the instrumental variable and the error term are not correlated. We cannot test this instrument exogeneity requirement. It can be only argued by common sense or economic theories. In our example, if we use the parent's education as an instrumental variable for the worker's education, we must argue that the parent's education will not affect the worker's wage directly or indirectly through any channel other than the worker's education. It implies that the parent's educational level should not relate to the worker's ability or personality. This is the hardest part to justify a valid instrument. The idea of the instrumental variables method is to replace the endogenous variable with the part of its variation that can be explained by the instrumental variable. That part of the variation is the fictive value from the regression of the endogenous variable on the instrumental variable. We call this process the two-stage least squares. In the first stage, we regress the endogenous variable, education in our example, on the instrumental variable, parents' education, and other exogenous variables in the model. We obtain the fit value. In the second stage, we replace the endogenous variable education with the fit value from the first stage regression and run an OLS estimation. The estimated coefficient on the fit value is the two-stage least squares estimator, with the parent's education as an instrument for the worker's education. We can think of the variation in the endogenous variable education in two parts. the exogenous part and the endogenous part. We isolate the exogenous part of the variation in the first stage regression and only use it in the second stage regression. We can see that the exogenous part of the variation comes from the fit value in the first stage regression. The endogenous part of the variation has been removed. As a result, when we replace education with its exogenous part of variation, it is no longer correlated with the error term. So the second stage regression gives us an consistent estimate of the return to education. The two-stage least squares estimator is a consistent estimator of the true parameter. We can prove it mathematically. Suppose the regression model is y equals x multiplied by beta plus epsilon. X is the endogenous variable and z is the instrumental variable for x. All are in matrix form. In the first stage, we regress x on z and write the OLS estimator alpha hat. We obtain the fit value x hat. We can define the projection matrix Pz. When the projection matrix is multiplied by x, it gives the fit values in the regression of x on z. It is also the projection of x onto the z space. As we mentioned, the purpose of the first stage is to keep only the exogenous part of the variation in x. We can write the fit value as Pz times x. In the second stage, we regress y on the fit value x hat, and we obtain the two-stage least squares estimator. We write out the estimator using the projection matrix. Because the projection matrix is symmetric and idempotent, we can simplify the two-stage least squares estimator as follows. Next, let's prove it is a consistent estimator. We replace y with x times beta plus epsilon. Then we find that the two-stage least squares estimator equals the true parameter beta plus a second term. Since the probability of z prime times epsilon equals 0 by the instrument exogeneity requirement, we have the probability limit of the second term is 0. As a result, the probability limit of the two-stage least squares estimator equals the true parameter beta. That is to say, it is a consistent estimator of beta. Coming back to our example, we have seen several possible instrumental variables for the endogenous variable education in the wage equation. People often use the worker's family background, like their parents' education level, the number of siblings, or the birth order as instrumental variables for the worker's education attainment. The geographic characteristics are also commonly used as instrumental variables for education. For instance, the distance to a college from home, or whether living near a 4-year college, can be seen as a possible instrumental variable. They are not likely to influence the worker's wage directly or indirectly through any channels other than through the impact on the worker's educational attainment. We will discuss the instrumental variables method in Stata in the next topic. Thank you for watching this video. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.